Swayam Prabha. Digital India. Educated India.
Hello. So welcome to yet another lecture in this course of astrochemistry. Today we'll be looking into lecture 5. So as a recap from the last lecture, in the last lecture we discussed how the lighter elements, hydrogen and helium and very little lithium also, can be synthesized after a Big Bang, and this involved the fusion of nuclei, and so it is called as nucleosynthesis. We discussed this in the last class, and this was followed by our introduction into what are called as interstellar clouds, where these interstellar clouds can have some atoms, elements, molecules, compounds, and some ions as well, along with the presence of various cosmic rays and a stream of electrons. So we stopped the last class by looking into the imbalance between the kinetic energy due to the molecules of a cloud, molecules or the ions of the atoms of an interstellar cloud, how there's an imbalance between the kinetic energy and the gravitational potential energy holding the cloud together. So this results in a massive turbulence, and the cloud shrinks. The interstellar cloud shrinks to a hot core. It shrinks to a very hot core. Okay, right? When I say hot, I'm talking about temperatures of the order of tens of thousands of kelvins. Okay, right? So the cloud shrinks to a hot core, and this core, this hot core, is what is called as a protostar. And this eventually, gives birth to what is called as a star itself. So this is how a star is born in space. Okay, right? So this hot core is what is called as a protostar, and starting from the Big Bang itself, right? Starting from the Big Bang itself, this whole process, for the entire imbalance between the kinetic energy and potential energy to play out, it takes approximately 10 to the power 9 years after the Big Bang. Okay, right? So after t equals 0, by Big Bang, I'm talking about t equals 0 as defined as the starting point for Big Bang. So we have this core, this very hot core. Now, around this core, there are lots of molecules, atoms, ions. They keep rotating around the core. Okay, right? Around this core, or we can call this protostar. Lots of molecules, ions, atoms, etc. keep rotating around this core. Now, this results, okay, right? So around this core, but why do these molecules rotate around this core? Because, see, what has happened is that some molecules and atoms have gone inside, have become part of the core. But there are other molecules which are still under the gravitational influence of the core. Even though the core has shrunk, even though the gravitational influence in the cloud is much lesser now, despite that, many molecules will still linger around this protostar, this hot core. Okay, right? So this results in a disk of atoms, molecules, and ions around the hot core. All right. So what's our understanding so far? We know that a protostar is born, but surrounding a protostar, due to the influence of gravity, there are still lots of molecules and ions, rotating around this hot core. Okay, right? And these molecules are actually very important. Okay, it is not just the protostar, but these molecules, as we shall very soon see, are very important to understand the concept of molecular evolution itself. Now, and once this disk, okay, this disk of molecules is formed around the protostar, there is a constant transfer of matter between the hot core and the disk. I mean, this is to be expected, right? This is to be expected because there are some molecules and ions as part of the core, and there are some molecules and ions as part of the disk itself. Okay, right? So there is constant transfer of matter between the core and the disk. Now, what molecules become part of the core and what become part of the disk? That is critical to how molecules evolve in space. We shall look into that. So what molecules? So the lighter elements for example, we're talking about hydrogen, helium, and some refractory, I'll write it more cleanly, refractory molecules which can withstand the heat. Heat in the core, they become part of the protostar. And eventually, subsequent nuclear fusion happens in the protostar itself, such that, you have what is called as stellar nucleosynthesis, and within this core, newer elements are formed, and the protostar eventually becomes a star. But what happens in the disk is even more interesting. The molecules in the disk, right? Let me just say, the atoms / molecules / ions in the disk, I mean, they can continue to be part of the disk as long as, the they are held under the influence of the gravity of the protostar. Okay, right? However, some of them can escape too, right? Some may escape the gravitational field of the protostar. Now, this event, the escaping the gravitational field of the protostar, is an exceptionally important event, in our celestial understanding. Okay, right? So, fact that, some of the molecules may escape and fly as debris, okay, from escaping from the gravitational field of the protostar. This results in the formation of a lot of celestial bodies. Okay, right? This is a very important event. This is a very important celestial event which has tremendous implications for the formation of life itself. Okay, right? So what happens to these molecules ions? They escape such that you can have the formation of what are called as comets, asteroids, and planets themselves. Okay, right? So this material eventually, which escapes from the hot core of a protostar, that is what becomes comets, asteroids, and planets. Now, these are phrases, you must have all heard, right? Even in everyday parlance, you talk about a comet hitting a planet. You also talk about asteroids and asteroid belts. And you lastly talk about planets. Planets we've been studying since primary school. Okay, right? So the idea is that these comets, asteroids, and planets are eventually, made up of the atoms or molecules which escape the disk space from a protostar. Is that fine and clear? So this is how, starting from some clouds of molecules, atoms and ions in space, we get to form planets, asteroids, and comets. I will of course, like talk about each of them in great detail, right? In the coming classes as well as in this class, right? Yeah. So that we understand how each of these different milieu, the protostar, the disk space, and then the planets, asteroids, and comets, how they give scope for different types of chemistry, and how understanding them, enhances our knowledge of chemistry itself so vividly. Okay, right? And of course, not all molecules may escape to form these. Some of these molecules, okay, right? Some stuff. Now, by stuff here, I only mean a combination of atoms and molecules or ions. Okay, right? Some stuff may escape and stay as, just interstellar dust and gas. Stay as dust and gas. Okay, right? So I start this line from here. Okay, right? So some molecules escape the gravitational field of the protostar to eventually become comets, asteroids, and planets. But some molecules may just stay as dust and gas. Okay, right? I mean, I haven't precisely defined what exactly dust and gas means, but hold on. I will do that either in this lecture or next lecture. What we shall now do is to understand what these planets, asteroids, and comets are, their molecular composition, the distinction between them, and how they provide scope for varied chemistry. Okay? We'll start with comets. What's our understanding of a comet? So, what's our understanding of comet? It's just some celestial body, We typically see a comet with a tail, right? We see that a comet typically has a tail, and the comet is something that just comes from out of our atmosphere, falls on to the atmosphere, and then eventually, hits the Earth. That's our understanding of a comet. But what is it made of? Why is it relevant for chemistry, etc.? Those are the questions we'll be looking into now. Now, the comets, right? Yeah, the comets contain icy material. Okay, right? For example, material of volatile molecules, volatile small molecules such as HCN, methanol, carbon dioxide, CS2, etc. Okay, right? The key thing is that, see, by the use of my phrase ice here, okay, right? I refer to a collection of loosely bound molecules. Okay. Now, if they were much stronger and then like more tightly bound, we'll be using the phrase rocky. Okay, right? Rock is much harder and held by a much stronger forces than an ice, which of course also refers to a collection of molecules, but these molecules are loosely bound than a rock, than you would see in a rocky material. All right? Yeah. So it contains icy material of these molecules, and not just these. In fact, you'd be surprised to know that even glycine, the amino acid, right? The amino acid, which is quintessential for our survival as human beings, right? Yeah, even glycine has been detected. And so you have like icy material of some of these molecules, and you also see molecules floating around in a gas phase. Okay, right? In fact, it is this weakly bound system, and some gases hanging loose. Okay. Which results in the comets typically having a tail. Alright, so we can sometimes see comets even with the naked eye or with a telescope, right? So when most often than not, when our observation of comet involves leaving a trail of gases, such that you kind of notice that it has a tail. Okay, the tail is because it consists of loosely bound material in the form of ices as well as gases. All right, yeah. Now the last thing I want to talk to you is about comets. When you observe a comet using a telescope, you notice a comet as a fuzzy object, not as a single bright point. Okay, why do we see it as a fuzzy object? Because it has like loosely bound gases and solid material. Okay, right? So when observed, via a telescope, a comet appears, okay, right, fuzzy and not as a bright spot. Not as a bright spot usually, okay, right? So this is about comets. The next celestial object that we shall be looking into is asteroids. Now, what is the distinction between an asteroid and a comet? Asteroids, they contain rocky refractory material. Now, what do we mean by this? What do I mean by this? Now, if you go back to a comet, we see that in a comet, the molecules are loosely bound. The molecules are loosely bound, and these are all small molecules. But, when we talk about inorganics, when we talk about, like silicates and some metal oxides, etc., which can form huge giant ionic solids, or some molecular solids also in some cases, right? And they are strongly bound via ionic bonding, right? You get the formation of these rocky refractory materials. So they all come together to form what are called as asteroids. And the important point to note is that it's not just these rocky refractory material, but some organic material, okay, right? Some organic molecules are also adsorbed onto the surface of these rocks. So it's not just these inorganic materials, but quite a few organic materials, organic molecules are also absorbed onto these rocky surfaces. Okay, but notice the point. These organic materials, they're not actually absorbed inside these rocky materials. They're weakly adsorbed. In other words, the absorption is just one layer deep. Okay, this has tremendous consequences for how molecules which are significant for the origin of life came to Earth. Okay, we will discuss them in a subsequent lecture. But for now, please note that many organic molecules are also adsorbed onto the surface of these rocky materials as part of the asteroids. All right, yeah. In fact, most noticeably, okay, right? The sugar, ribose. Homework, what is its structure? We'll look at what the structure of ribose is in the tutorial. Okay, right? Ribose was actually detected, okay, right, in an asteroid in 2019. All right. So, and then what about the dimensions of an asteroid? An asteroid can be as small as something 1 meter, or it can be as large as having a diameter of 1,000 meters. Okay, and another point about the asteroids is that when seen using a telescope, the asteroids, okay, right, they appear as bright spots more often than not. This is a key way, via which we can distinguish between asteroids and comets. Okay, appear as bright spots. Okay, so this is the key understanding about asteroid. And yeah, you all must have also heard about the phrase meteorites, correct? In fact, when asteroids land on Earth, we don't use the phrase asteroid itself. We only call meteorites. So what's a meteorite? Any idea? Based on your understanding of popular astronomy, astrophysics? A meteorite is nothing but a chunk of an asteroid that has fallen on the Earth's surface. Okay, so this is all a meteorite is. So we've looked into what a comet is, what an asteroid is, and as part of an asteroid, we also understood what a meteorite was. Next, we shall look into what planets are. Okay. Now the planets are also rocky materials, right? Yeah. Organic materials and lots of gases, which are much larger than an asteroid. Not just larger, they're also much more symmetric. So in the tutorials, we'll look into why is it that a planet is much more symmetric than an asteroid. All right, yeah. But for now, we understand that a planet is nothing but a much larger version of an asteroid, which is much more symmetric. For example, in our own galaxy Milky Way, we have all the planets. Although they're not perfectly spherical, they are like they have an ellipsoidal shape, right? Most planets are almost a sphere, but they are significantly more symmetric than the asteroids, which are asymmetric. Okay, right? And see, if you notice it, I intentionally mentioned about rocky materials, organic molecules and materials, and lots of gases. But what about liquid water? Liquid water is something very special to our Earth. And in the case of Earth, there is also liquid water, but it is very unique and special to our Earth, okay, which makes us all live on Earth. Okay. So next, along with planets, what else should I be discussing now? I mean, the planets are formed, but along with Earth, what always comes associated with the Earth? The satellites and moons, right? The natural moons. Where did they come from? How did the moons of Earth, I mean, not just Earth, any planet, how did they come about? Well, there are two leading theories. The satellites of these planets, they come about in the same way. In the same way, the disk of a protostar gave birth to planets, etc. The same way, because the planet is a much larger entity, its gravitational pull is significant. So there were a lot of molecules, atoms and ions surrounding the planet also. So once they escape the gravitational field of a planet, right? So they give rise to much larger chunks called as moons. This is very similar to how the planets themselves were formed from protostars. Okay, right? So it's very similar to, the mass, a large amount of mass accruing together, and once sufficient mass is built up, they escape the gravitational field of the planet itself. So it's very similar to how the planets, asteroids and comets, etc. are born from a star, that the moons of planets are also formed. Okay, right? That's the idea. So now what have we looked into so far? We have now looked into the idea of how, various celestial bodies that we commonly hear of, the asteroids, the comets, and the planets, and along with the satellites, how they've all formed from a star. Okay, right? We have looked into this. Not an important point. The important point is that each of the celestial bodies, they give us a tremendously different scope to understand chemistry. For example, if we deal with a comet, right? If we deal with a comet, the chemistry in the comet is predominantly guided by that of very weak chemical interactions, because the ices as well as the gases are loosely bound. They are loosely bound, and so the comets when they fall on Earth, they deposit, materials very readily. Okay, right? But what about the chemistry for meteorites? The meteorites involves molecules which are strongly bonded. So from these strongly bonded materials, right, the meteorite or an asteroid, when they fall on Earth, right, they are the major source of transferring, lots of rocks and a lot of inorganic material on Earth. Okay, and lastly, we have the planets themselves, right? We have the planets themselves, which have a combination of rocky materials, organic stuff, and gases too. So just a simple star, while it is forming, right, when it is in the stage of a protostar, how that gives rise to so much variety of molecules in all by the process of the gravitational field of the parent larger protostar, right, being violated. Once we cross the gravitational field of the protostar, we get tremendous scope for chemistry. Okay, right? So the next idea we shall be moving into is the concept of what is called as an interstellar medium. Okay, I will talk about that now. So we now understand that surrounding every star there is a circumstellar disk, right? And this circumstellar disk eventually gives rise to a lot of celestial objects such as planets, asteroids, comets, etc., etc. Now in this disk, right, in this circumstellar disk, there is matter which is under the influence of the gravitational field of the protostar. Okay, right? So now if we exclude this disk space, okay, after excluding the disk space, the distance between any two stars of the space, okay, right, not the distance, the vast space excluding the disk space is what is called as the interstellar medium. Now this is a very important region. This is a very important region of space where a lot of chemistry happens and a lot of molecules which play key roles in the origin of life are actually getting formed in the interstellar medium. So we shall look into the chemistry of we shall begin looking into the chemistry of interstellar medium in the next lecture. To sum up, in today's class we looked into how various celestial bodies such as planets, asteroids, and comets were formed from the circumstellar disk of a protostar, and how they present different scope for chemistry. For example, in the case of a comet, we have the transfer of gassy material onto Earth, and but whereas a meteorite presents with the scope of a lot of rocky inorganic solids which are transferred to Earth. Okay, so on this note, I end this lecture, and we shall begin our next lecture with an understanding of what the interstellar medium is. Thank you.